These are notes 14.3 for BC Calculus. We're going to continue on slope fields and do a thing called Euler's method today. Let's start with this diagram. You can see we've got a lot of dots on here, and we're going to create our own slope field given this differential equation, y prime equals 1 over x. Yeah? So note the scale here. This is where x equals 1. And if we look at our equation, we can do some quick little math. We probably don't want to or need to do a table for this one. But you can see that just like we talked about yesterday, for every x value, we're going to have all the same values. When x equals 1, each one of the slopes are going to be the same. Next vertical line over here, when x equals 1.25, they're all going to be the same. 1.5, they're all going to be the same. So let's just start with the easy one. When x equals 1, 1 divided by 1 gives us a slope of 1. So let's go ahead and do our little tick marks here with the slope of 1. Slope of 1, it's going to look something like these. Just fill all these in at about the same slope. Since this is a reciprocal graph, the next easy one for me to do is just go back over here to 0.5. When x equals 0.5, we're going to take the reciprocal of that and get a slope of 2. So we're going to be twice as big as this one. So our slopes for each one of these, all being the same, are going to be slopes of 2. And by the same token, over here, if we go to x equals 2, this is going to give us a slope of 1/2. So we're going to come in here, kind of look at this as a slope of 1/2. That's 1, so we're going to go half of that, and just make all of our little tick marks here at 1/2. Oops, I went the wrong direction. How about that? Obviously, it's not negative 1/2, but positive 1/2. So each one of these, again, will be 1/2, 1/2, 1/2, 1/2, 1/2, and 1/2. Okay. Maybe a little jumping around. Of course, 1/4, the reciprocal of that would be 4. So we're going to go a lot steeper over here for all of these at 1/4. Reciprocal of 3/4, or 0.75, would be 4/3, so a little bit more than 1. So there's our slope of 1. We'll just go a little bit more than 1 for each one of these, trying to make them all about the same. 1.25 would be 5/4, so reciprocal of that would be 4/5. So we're going to go less than 1, just slightly. Try and make them all the same, just a little bit shallower than the previous one. This would be 3/2. Reciprocal of that would be 2/3. So we're just going to slowly go more shallow for all of these, and then the next one kind of the same thing. This would be 7/4. Reciprocal of that would be 4/7. So on. You can kind of see this one there. So that's our slope field. We're going to repeat what we did yesterday by sketching the graph of the solution starting at 1, 0. When x equals 1, y equals 0. So we're going to start right here. Okay. And again, we don't have to necessarily start on 1. We could start anywhere in here. And we're not connecting dots. We're just kind of following the flow of this. And kind of looks like going down in this direction. We're going to kind of get steeper and steeper and steeper. Probably go something about like that. It's a little steeper. And then when we go in this direction, it's going to want to level off for us. It's going to go, of course, we're at a slope of 1 here, but then less than 1, less than 1, less than 1, when we get to here, we're going to have a slope of 1/2. So each one of those values going to kind of cause us to go in that direction. Okay? And that's one solution on this slope of field. The solution that starts here at y equals 1, or excuse me, x equals 1, y equals 0. Next, let's look down here where it says algebraically, let's find a solution to this differential equation. We're given y prime equals 1 over x, so all we need to do is integrate this, take the antiderivative, and this is going to give us the antiderivative of y prime. Of course, will just take us to y. And then this will be the natural log of the absolute value of x plus our little buddy c. From here, we'll use our initial condition, y sub 1 equals 0, to solve this. We'll get 0 for y, the natural log of the absolute value of 1. We'll add that to c. This, of course, is 0, which means c is also going to be 0. So, finding the solution to this algebraically, this is the curve, the natural log of the, y equals the natural log of the absolute value of x. Okay. Now, we're going to use this same graph to do something called Euler's method. It's pronounced Euler, even though it's spelled this way. And let's just go ahead and stop here and go to page number 2. And this will give us a little bit of an explanation before we actually apply it on the next page. Okay. So, Euler's method. Euler's method uses little segments from many tangent lines to estimate the value of the function. So we'll see what happens here is we'll start at this point. That is the point where x in this diagram, they use x 0, y sub 0. So this is the initial value here where x was some number, 1, 2, 3, 4, 5, 6, doesn't matter. But when we put that in the equation, we got y sub 0. From this, you can see that a tangent line was drawn. That tangent line was used to estimate a different value. We've done this before. Use the tangent line equation to estimate a value at a different point. Okay? In this case, that tangent line was used to get this value here at our second x value. And what Euler does is it says it doesn't do what we've done. We've done this hundreds of times already. Just use our tangent line, find the slope of the instantaneous rate of change, the slope of the curve, the derivative at this point, evaluate that, write a tangent line equation, come up with a new value for y using that. But as I was getting to, Euler doesn't just stop there. Euler says, okay, now that you got this new value, let's find the slope of the curve at that x value and draw a new linear approximation here. Okay? So it's using this slope at that point, and you can see another segment is drawn using the slope at that point, which gives us this. And each one of these is using the previous x plus a common value h as this on this diagram, which we all know as dx. This is the from the initial value of x to the next value is x, the initial value plus dx, and then we're going to add dx to the second value and get another value, x2. We're going to put that in the equation of this tangent line. Then we'll use the slope of this point on the curve to draw a new line or linear approximation. They're not necessarily tangent lines because they're not on the curve, but that's what Euler's doing. He's using all these lines to approximate the curve. And this, of course, would give us x2 plus dx, we would use this new x value to continue on if we wanted to draw our tangent lines. You can see it's not going to meet the curve exactly, as we do have these values in here for h that kind of give us away from the curve. Our knowledge of tangent lines and the curvature of a line, if the tangent line is below the curve, we remember that this estimate is going to be too low. If we had a different shape to our curve and our tangent lines were above, then our estimates are going to be too high. Remember, that all goes back to concave up, our estimates are all going to be below the curve. Concave down, our estimates are always going to be above. Yeah? So here's what Euler's formula does. It says the next y value that I'm looking for, y sub 1, is going to use the previous y value, y sub 0, and then add a change into it, a change in y. It's adding this amount of change each time. We're changing y here. And then we recalculate that. And from this y value, which they call as y sub 1, they're going to use this line to find a new y value. All of these links here are dx, 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 to come up with our new x value, x1, x2, and x3. Put that in our equation, and that's going to give us each one of these new y values. Now, let's rewrite this a little bit so that it kind of follows what we have up here. This is going to be the next value, y sub n, is always going to be the previous value, y sub n minus 1, plus the change in y, dy. This is a dy, and this is a dy. They're not all the same like in our dx's. They change based upon the slope. Isn't that the slope of our curve? So let's rewrite this one more time here. Y sub n equals the previous y value plus this dy. What is that? Well, it's going to be the derivative of our function with the input value of the previous x value, and we know that we have functions that are not only dependent on x but also on y in our slope fields, so we're going to put both those in there. Okay. And that's basically Euler's formula. I do want to show you this written another way because some books do write it a little bit differently than this, so you're used to the nomenclature. We could also say the next one is y sub n plus 1. And this, of course, then would be y sub n plus f prime evaluated at x of n, y sub n dx. Dx is the change in x, delta x, which is listed up here as h, and a lot of books use h in there as opposed to delta x, or use both of them, but that is this distance here that we're going and moving. And that always can be calculated by taking x of n, the one we're looking for, and subtract our initial x value, and then divide that by the number of steps that we want to use to calculate this. Okay? If we want to use 1, 2, 3 steps, we take x of n, this last x value, and subtract the initial value, divide that by 3, and that would give us how long each one of these h's are. It's going to be a constant length. Okay? Now, before we do any more calculations on this, let's just point out here, part 3. We're going to go back and flesh this out, but let's look at this. In order for Euler's method to be used, both the differential equation, or y prime, and the solution function must be continuous on the given interval, not over all reals, but over whatever interval this is. If we have a problem where it's not continuous, or, well, if it's not continuous, let me say, it will be a problem. All right, so before we do 4 and 5, let's go back to the previous page and take a look at this one and use Euler's method to estimate this. Okay, so what we're going to do is we're going to estimate the value of this function using Euler's method at x equals 2. We're going to find this y sub 2 value. Y sub 2 value looks like it's going to be up in this area somewhere. Let's see if we can get to that. Okay? That's our y prime equation and our initial condition. All of that's same as what we had before. When we do Euler's method, what we're going to do is a table. That means even people with last names, maybe just for example, just to make up a name like, say, Henke, or maybe first names like Andrew, those people, they're still going to have to make a table to use Euler's method. So let's be sure that everybody understands Euler's method. There's several steps to it. We're going to record this all in a table so that we can get full credit for this. So let's explain what's happening in our table. We've got x values that we're going to put in here. We're going to calculate y values. We're going to also calculate y prime, dx, to find our dy value. Okay? So let's look at this. We know we're going to start here at our initial value. And it's supposed to be an I. Initial value. Our initial value for x is 1, and we know y was 0. Okay? Now, we're going to put this x value in y prime. Y prime is 1 over x. 1 over x is going to give us 1. We just put that x value in here. 1 over x is 1. Now, dx. Let's talk about how we calculate dx. That was on the previous page. Remember, dx was that x of n minus x of 1 divided by the number of steps that we had. Okay? In this case, our x of n is 2. We're going to be using 2 and 1 for the initial value of x and the value that we're estimating it for. So we've got 2 minus 1, and then they gave us the number of steps. And they said, let's do this in 4 steps, which means our dx, or delta x, is going to be simply just 1/4. Okay? So 1/4 is going to be the same for all of these, or 0.25, 0.25, 0.25, 0.25, 0.25. dx is not going to change. Okay? It will not change. dx is going to be the same. Okay? And then we need to find dy. How are we going to find that? Well, it's based upon these values here. Let me go up here and just show you real quickly. We know that dy dx is the same thing as y prime. If we want to find dy, sure looks like a little bit of algebra. Don't we just multiply both sides by dx? And that'll give us dy equals y prime times dx. And that's what we're going to do here. We're going to take these two columns and multiply them together. dy is going to be our y prime value times dx. 1 times 0.5 gives, or 0.25 gives us 0.25. Okay? Now, let's go back over here. Our next x value. This is real simple. Remember, dx doesn't change. dx is the change in our x. So the next x, let's quickly go back to this diagram. Remember, here's our first x value. To get our next x value, all we do is go h units this way or dx units that way. We just add dx each time, and that gives us our next value. So we can actually fill out the rest of the table here for our these. This will be dx plus the initial value. This will be 1.25. That is one step. And then we'll add 0.25 to that and get 1.5. And again, 1.75. And again, we'll get to 2. 1, 2, 3, 4 steps. x1, x of n. Okay, so we've got these two columns done in our table. Now, let's go ahead and calculate our y value here. Okay? In order to calculate the y value this time, what we're going to do, oops,